our class. I will show you later on the QR code. Alright, so now we in the week 9, alright, you can see in the week 9 we need to cover conservation of mass and energy equation, right? And week 10, steady uniform flow and steady non-uniform flow and momentum equation. So inshallah, I will cover this conservation of mass and energy equation in this lecture. So previously we have learned about the integral form. Alright, remember chapter number 4 related to integral form. Why we are interested, why we need to learn the integral form? So the answer is the integral form is interested by engineering field to solve the complex problem, right? Some said that the integral form is the solution form. The solution form means you integrate from the small indefinite particle, you integrate, post the integration, you will get the whole solution for the whole model. Right? Remember the integration, we find the whole area or the whole volume. So you use the integral form to find the complex solution. In the integral form, there are two categories, right? You have the system and the control volume that we have learned previously. Let me draw so that you will understand clearly. Okay. Right. So, remember our last class, we learned about the integral form. In the integral form, we have two types, right? We need to solve, which is the system and the control volume. So what are differences between system and control volume? Anyone? I think we have discussed previously in the last class, right? What are differences between those two? The control, the system is referred to, right? Is referred to Lagrangian description. Remember, we have two types of description. Lagrangian description, where it focuses more on time. The control volume is Eulerian description. It focuses on the space and time, which is X, Y, Z, and time. So this is Lagrangian and this is Eulerian, right? Normally, scientists prefer this one to be expressed in terms of Eulerian, which is space and time. This is considered only time. I mean the time derivative. This is considered of time derivative and the space, which is X, Y, and Z location. So normally we prefer, or engineer or scientists prefer to express the system to be converted into control volume, which is space and time. So this is, I would like to recap back, right? The system is where this is the particle, right? It is moving. This is particle at time 1, this location, at time 2, this location. So this is basically the system. The system is moving with time. However, for the control volume, right? For the control volume, this is we consider there is the box, right? And at time of 1, this particle enter this region and then leaving this region. This is time 1, this is time 2. Our concern is only the control volume here, all right? So we are referring this X and Y and Z directions, all right? This is space. You remember we have the control volume. This is considered of space and time, all right? So we only focus on particular region, the fixed region. There is no motion of the control volume. However, the system is in motion. So in order to convert system to control volume, we use one theory, which is Renault transport theorem, RTT. Thank you, Amirul. Now you understand, yeah? Renault transport theorem convert the system into control volume. Let we expand further our understanding. This is, for example, this is, right, this is a pipe flow. Alright, this is water flowing through from the left to the right, water, H2O. And by using the control volume definition, we actually draw control surface here. That means we focus this region only. This is our region of interest. We call as control volume, right? This control volume has control surface. This surface here we call as, this dotted line we call as surface, control surface. So in the control volume, we have another component we call as control surface, CV and CS, right? In control volume, we define as the rate change of control volume. For the control surface, we define as the flux coming into the system and the flux coming out to the system. All right, what is the flux? The flux, right? You must be wondering, this is the flux, F-L-U-X. The flux is actually the extensive property coming to the system and leaving to the system. Remember, I give you one quiz to define the flux, to define the extensive property, intensive property. So the flux is actually the extensive property coming into the system and leaving to the system. This is flux, right? And as well as we have the rate change of control volume. For example, okay, let me draw. For example, there is a water coming through this inlet. This is point number 1 and this is point number 2. And the water coming, you can see the level of water. All right, for example. So this level of water we call as the rate change of water level. And we have to plus the flux definition, which is the extensive property coming to the system and leaving to the system. Thus, the Renault transport theorem, we simplify into this term, right? This is our Renault transport theorem. What Renault transport theorem said that, all right, the total derivative, right? I think this is not enough space. The total derivative d over dt, the extensive property of the system, and is extensive property. Remember, extensive property is the property related directly to the mass. Alright, for example, what the property related to the mass? Volume, mass, momentum, or energy. So all these we call as the extensive property, the property directly related to mass. I would like to question you guys, what is the example of intensive property? Please comment there. I want every one of you, please comment one simple example of intensive property. Amirul, anyone? Please comment in the chat box. I want one person to comment. Yes, correct. Temperature, pressure. Okay, next, I don't want the temperature. There are many of the intensive property. The property not related to, yes, color. Property hardness. Property not related to the mass. Whatever the biggest or the smallest mass, the property will be the same. That's why we call as the intensive property. Thank you everyone for answering, Eugene, viscosity. Alright, so all these, the property not related to the mass. Right, so now we consider the property. Thank you, Zara. Property directly related to the mass. So this is end of system. For example, momentum or mass directly related to the mass. Right, the total derivative over dt end of the system is actually equal to the small d over dt rate change of control volume. Remember, we have the CV, control volume. So we need to find the rate change, what happened of the water level over the time. Is it the water level rise or drop? So this is the first term, control volume. Integral of control volume, intensive property, rho d v. This is volume. Plus, remember, just now I talked about there are two types, control volume and control surface. This term related to control volume and the other term related to control surface. So in the control surface is the intensive property rho v dot product, and this is a unit vector perpendicular to the, alright, Hakim, all of these are flux, right? Right, this term, okay, Amirul, the second term reflect to the flux. Alright, I will tell you, this term, the second term reflect to the flux. Right, this is the equation dA. Right, remember that this is very important equation to convert. You can see this is the system. You can see the first is the system. This is system. We convert it into control volume. You can see this is control volume. So this is where we convert from the system to the control volume. However, control volume have two types, two definitions. We have control volume and control surface. Alright, for the control volume, we care on the rate change of water. For example, water rise up or drop. So this is the term, the first term. And the second term is the flux term. Alright, we refer to the flow of the extensive property coming and going out to the system. If you look at here from this definition, we have the surface area. We call as, you can see the surface area, cross-sectional area will be like this. if you see in this direction. Same goes to this direction. You will see the surface area will be the circle. The flux is, by definition, is the flow perpendicular to the cross-sectional area. So you can see this is dA. This is an unit vector perpendicular to the surface area. You can see this term. This is dA and this is N. Alright. So all these directly related to the RTT, Renault Transport Theorem. So do you guys understand how to convert from the system into the control volume using the RTT, Renault Transport Theorem? Do you guys okay so far? Okay, please respond. I want to see. Okay, all right, thank you. So the next is, after we understand the RTT, Renault Transport Theorem formula, this is the formula, yeah? The curly bracket here is the formula. And then we try to apply to the extensive property number 1. Extensive property number 1 we call as the mass. Remember, extensive property, we have many extensive property. One of them is mass, right? So we apply to the mass. Once we apply to the mass, it becomes conservation of mass. Now you can see there is the relation to the RTT, where you learn the conservation of mass because of the extensive property. One of the extensive property is mass. So you apply here, this is actually N. Now they replace the N with M of the system, equal to, this is the formula, they convert it, right? Basically, this term is the mass. Why mass? Because density equal to mass over volume. So in order to get mass, density multiply with volume. You can see density multiply with volume to get the mass. So this equation the same with this equation. However, this term is related to the integral form. Alright? So from here, for a steady flow, this simplify to, remember, what is steady? What do you understand of steady flow? The steady flow is mean by any property, whatever temperature, pressure, viscosity, the mass flow will not change with time. All the property constant, fixed. So when there is the relation of time, it will equal to 0. There is no change with time. We call as the steady flow. The change of d over dt of the property here, right? Whatever property here will become 0. Remember, we have the Renault Transport Theorem, the full here. Whatever change of time equal to 0. So this term equal to 0. This is not changed with time, so there is a value here. So this term with change of time equal to 0. Now you get this equation, you simplify this equation, 0, 0, definitely you will get this equation. Can you see that this is CS, this CS, this is density, all right? This is density, And this is density, this is velocity, this is N, dA. All right. Do you notice that we have this intensive property? Right, but here we don't have any intensive property. Before we proceed further, right, this N we call as the, let we recap here. Capital N we call as the extensive. And this N we call as the efficiency symbol is the intensive property. There is the relationship between these two. In order to get this intensive property, the formula is like this. Extensive property divided with mass. So that means that property we remove the mass. So there is no property directly related to mass because we have cancelled the mass. We divide the mass. That's why this become intensive property. We don't want any property related to mass. So that's why we divide with mass. So this is the formula, right? From this equation, remember, this is we call as 0 equal to 0 plus control surface intensive property rho v dot product. Why dot product? Because we consider only the flow perpendicular to the cross-sectional area. And this is unit vector, yeah, only direction concerned. Alright, so this equation, there is the intensive property. However, this don't have any intensive property. Remember, we focus on conservation of mass. So conservation of mass, in order to replace the intensive property, remember intensive property is extensive divided with mass. So what is the extensive, which is mass? Divide with mass. So what's the answer? Mass divided with mass, you get 1. Alright. So Amirul understand. So why don't we replace this term with 1? Then definitely you will get 1 B dot N dA. Now you can see this equation is the same with this equation. Yeah? Okay. So far, so good. Okay. You get how to get the conservation of mass using RTT. All right. Do you have any questions so far? Anyone? Okay. So far, okay. All right, Eugene, how? Fikri, thank you. So now you understand, yeah, how we apply the RTT into the conservation of mass. All right. So this step you understand basically. Now we further go to this step. All right. Okay. Remember that this step is simplification of steady flow, which is the change of time equal to 0. For example, we have one entrant and one exit. So this is, okay, this is, for example, this is control volume. There is the flow here and flow out. All right. This is cylinder. So In order to apply this equation into this form of model, right? I think this is not good. We try to improvise a little bit. Okay. It's okay. Okay, this is nice looking. Okay, this is the cylinder. The water coming in and coming out. Point number 1 and point number 2. All right. So remember that any flux out of the system is positive. Any flux into the control volume is negative. So let's we try to solve this equation. Right, this is control surface. We consider only the surface area. The cross-sectional area, when you look at here, it will become circle. Alright, this is considered as area 1 and area 2. So rho, point number 1, n is the flux, the unit vector direct perpendicular to the cross-sectional area. So this is into the system. So the flux here is negative. This is out of the system. The flux is positive. So negative n dot V dA. You need to plus point number 2, which is rho 2. This is only 1, this is 1, yeah. Or we can say that this dA we replace with area. Right? This is area number 1. Alright, rho and n. This is n for positive. And V2 A2 equal to 0. You try to simplify. You move this term to the other side because this is negative. Definitely you will get rho. This you try to rearrange alphabetically. A is the first term, right? A, 2, V2. All right. This n, we can consider that the velocity directly normal to the surface area. So this n we can omit. Basically, we have this one, right? Equal to rho 2 A2 V1n. Right? Now the equation the same with this equation. Right? This equation basically we call as the mass flow rate equation. Right? This is the conservation of mass. All right? And we also call this equation, this term, mass flow rate is equal to rho A P. This is mass flow rate, remember. All right? The mass flow rate only focus of any compressible flow. What are the example of compressible flow? For example, the gas, right? Or air. All this property we can easily compress because there is a change of density. All right, this directly related to the gas mass flow rate. When it is involved of water, incompressible, we call as the volume flow rate. Because density is constant. Remember that incompressible density is constant. For example, water. The water is hardly to compress. So the density is very hard to change. So the density 1 will have the same with the property of density 2. That's why we cancel off density. So that's why this is the volume flow rate equal to area times velocity. Right? So when the question asks how to derive the conservation of mass, you know how to derive, yeah? All right. So this is what we call as a conservation of mass for the non-uniform velocity profile, right? Normal case will be like this. All right, this is the pipe flow. Okay, this is, for example, the pipe flow. Due to the wall shear stress, the friction of the wall, the flow is non-uniform. Right? This is the velocity profile. This is the normal case in our daily life. The flow in the pipe, this is the pipe, will be like this. This is velocity profile. There is like this because we have the shear stress tau wall. We have the shear stress along the wall. We call as tau wall. Right? If the density is uniform, that means we assume this density is uniform like this. Basically, previously like this, yeah. We assume it is uniform like this. So you can see all the velocity uniform. This is uniform flow. Alright. So this you can see here, we call as the V average. This is V average. Average. If the density is uniform over each area with non-uniform velocity profile, right? Right, this you can see average can also be used, right? If the density is uniform. So then if the uniform density, you can move out density out because it is uniform or constant throughout the time. So the mass flux here is the mass flow rate. Remember previously we tried to solve the mass flow rate is rho A B. So we have the rho, we have velocity, normal, and area. Where Vn here is the normal component of velocity. And this one is directly related to volume flow rate, right? The volume flow rate, right? Remember that our previous equation, we tried to solve like this. Control surface, rho V and dA is equal to 0, right? This is the steady flow. So because of the one entrance and one exit, we try to solve rho 2, V2. Oh, this is not the V. First A first. A2, V2 equal to rho 1, A1, V1. Right? So here, the flow rates is the volume flow rate. So if this considered as the incompressible, you can see the density 1 equal to density 2. Cannot be compressed, cannot compress. normally they define the incompressible when the Mach number, when the Mach number is greater than 0.3. Alright, this is considered as incompressible. This is less than. Okay. When the Mach number less than 0.3, we consider as incompressible. Why less than 3? Because when the speed is low, there is no change of density. We call as the incompressible. So density 1 equal to density 2. So density 2 equal to density 1, we can cancel. That's why we get the equation A2 V2 equal to A1 V1. This term is equal to volume flow rate, right? So this term basically is the volume flow rate, Q equal to AV. Only apply for, remember, only apply for water or incompressible. Okay, so now I hope that you try to digest and understand. Next is, right, this is a conservation of mass. I will try to show you in the tutorial to get you more familiar. Alright, basically the same. Alright, next we go through to the energy equation. Right, so energy, why energy equation really important in our daily life? As you know that energy has surrounded us. You can see, for example, like aircon, the fan, we have the thermal effect. All this is the energy. All right, the light is the energy. So this energy is the extensive property or intensive property? Please comment there. Is the energy is the extensive or extensive property? Or please comment. Energy is intensive or extensive? Extensive or intensive? Okay, why energy? Why it is extensive? Please comment. Why it is extensive? Yes, energy depends on mass. Please prove. Is there any relation of energy related to the mass? Which equation? Energy related to mass. Okay, good. Next. Okay, good. Kinetic energy next. The very famous person, Albert Einstein. E equal to mc squared. Remember? Energy related to mass times the speed of light squared. So you can see that energy depends on mass. All right. So now we go to the extensive property number 2, which is energy. Extensive property number 2 is energy. Remember previously we learned the extensive property number 1, which is mass. Now we go to energy, which is extensive property number 2. In order to get intensive property, extensive property should divide with mass. So E divide with mass, you get small e. Right? The small e means over mass, energy over mass. Remember that energy over mass related to 3 terms. The kinetic energy, the potential energy, and the internal, the internal energy, right? So if someone asks you what is the energy of the system, so it directly related to three terms only. We don't care about the electromagnetic energy. For this course, you only focus on three basic of energy: the internal energy, the kinetic energy due to the motion. When there is motion, there is the flow, there is the kinetic energy. When there is the there is the change of elevation from H1 to H2, there is the potential energy due to gravity effect. And lastly, the internal energy. The internal energy is like this. This is the control volume. Under microscopic view, very small, there is the particle. Right? So what do you think under normal condition, the particle will behave like what? Please comment there. What the particle will behave under normal condition? There are many behavior. Please state, every one of you state any behavior of particle. For example, water. What do you think under normal condition, what the particle behave? What it will be? Okay, move freely. Okay. Next. Okay, collide with each other. Okay, good. That is good. Next. There are more. Collide, okay, correct. It collide, move freely, whatever. What do you think when it move freely? There is no traffic jam, there is no law on the road. What happened? Okay, collide, correct. Collide with the wall. Is it not collide with themselves? What? It's okay. The pressure is atmospheric pressure. There is a pressure. What happened? Under normal condition, we are exposed to the atmospheric pressure. Slide over each other. Is it vibrate? Is the particle vibrate? Is the particle vibrate or not vibrate? So the particle will vibrate, all right? This particle will vibrate. And then the particle will rotate. This particle, yes, it will rotate. This is particle. And it will rotate. The particle inside here will vibrate, will rotate, will collide. All this movement of the particle we call as the internal energy. All right. Remember that if we have the heat coming to the system, the particle will vibrate, rotate, move very fast. So that's why we call as the internal energy. Remember? All right. So this movement of the small particle we call as the internal energy. All right. So from this equation, right, we directly related to the Renault transport theorem, RTT. Remember that our RTT here, I tried to write down here. RTT, what's the equation of RTT? Which is d over dt n of the system equal to d over dt intensive property rho dv plus control surface, this is control volume, intensive property rho V dot N dA. So this is basic RTT, Renault transport theorem. Alright, in order to apply for the end of the system here is energy. This intensive property number 2 is energy. We try to replace here. Small e. We try to replace here e. So it turns out to be, alright, this is the rate change of energy. We can directly relate it to this one. Alright, this one we replace with this one. Right, so Q, the heat energy, remember we have the heat energy coming to the system, minus the work done on the system. That means the system produce the work. They lose the energy. That's why negative W, right, equal to this one. You can actually replace this one, yeah, which is intensive property is equal to D over dt, intensive property control volume E, rho dV plus control surface E V dot N dA. Right, basically this equation is the energy equation. Alright, so this one is still not expand further. You will see on the next slide. Okay. Now you see it is the same what I have explained. You can see Q minus W, D dt, E rho dV, control surface. Alright. Sorry, I left one term. We have the density. Remember, we have density here. Right, we have density. Density, we have energy, velocity, normal vector, and dA. So it is the same to this energy equation. Right? So Q here means the rate of energy transfer due to temperature. All right, we have the, for example, we have the water, you boil it, we call as the rate of energy transfer, rate of heat energy. Okay, Q is the heat energy. Don't confuse with the Q. This is Q dot. Q dot is the heat energy. Q only is for the volume flow rate or flow rate. Sometimes in the exam, they will simplify the term volume flow rate to be the flow rate. The same. The volume flow rate is actually the same with the flow rate. Alright? Volume, sometimes they omit, they don't want to specify. Only flow rate. This flow rate is equal to something. So please remember, volume flow rate is actually equal to flow rate. Okay, so the formula is Q equal to AV. When you see the Q dot is the heat energy. Right? And W. W is the work rate due to the work being done by the system. That means the system produce their own work. Now you try to figure out the system produce their own work. Right? So this mechanism you can see normal case in the turbine. For example, there is the water flow hitting the blade and produce the work. So the system produce the work. So it is release the energy. When it release the energy, it is negative. When it receive the energy, for example, it receive the heat energy, it is positive. Now you can see this term is positive energy because this is system. Sorry, this is control volume. It receives heat. it receive haba lah, it receive heat energy. So it receive is plus. And then it loss of work. This is negative. Right? So you can see that Q minus W, because Q plus minus W. This is the term of the energy. And the same thing that we have derived previously, this term is the RTT term, Renault transport theorem. Alright, I try to derive. This is in term of control volume, and this is in term of control surface. This surface here, we call as surface, right? Alright, this one they explain about the work term. Alright, why it is negative? As I mentioned, negative sign because of work done on the control volume. The control volume produce the work, produce the useful work lah. Okay. This work have 4 components. Alright, you can see in the control volume. I try to simplify this control volume. And there is a water level here. Okay. And there is the flow from the inlet to the outlet. Point number 1 and point number 2. Basically, there is the work. The system do the work. Alright. So they lose the energy. That means the water, for example, the water speed, velocity, this is logically, yeah? Velocity 1 is 100. What do you think happened after the long pipe? What happened to the velocity? The velocity will reduce or increase? Will increase or decrease? Increase or decrease? Christopher said reduce. Yes. Why do you think it is reduced? Why do you think? Because of friction. Remember, we have the wall friction along the pipe. Ada friction. Betul. Friction itulah. That friction is called the work. Nampak tak? They release the energy of the system. So, this term, you can see there's the friction here. We call as the shear friction, which is directly related to work of shear. Alright. So this term. And WS, work from the shaft. For example, the system consists of turbine or consists of pump. Pump or turbine, there is a shaft. Alright, the shaft is moving. There is the blade, there is the shaft. So the work here refer to the work of the shaft or work of the turbine or pump. So for example, there is the shaft. I try to draw nicely. Okay. Alright, there is the shaft. Okay, there is the shaft. Okay, this is the blade. So once the flow going in, it will rotate the shaft. This is work from the shaft, SH, directly related to this equation. Remember? Alright, so because of shaft, do you think the velocity will become lower? It will be very lower because loss of energy. And this one is the work directly related to the flow work, right? The work required to push the flow. work rate resulting from the force due to the pressure moving at the control surface. This considered as the flow work. The work flow, flow work, the work responsible to let the flow move. All right. So this you can see, this is velocity, and this is area, and this is pressure. All right. They using the pressure. All right. The system using the pressure to push the flow from point 1 to point 2. We call as the flow work. And lastly is the work related to the fixed reference frame. All right. So I think you previously considered that. For example, we have the reference frame, initial reference frame. So this one, if the control volume doesn't move, we have the work itself. If the control volume move from point 1 to point 2, there is the work. All right, remember, if the control volume move from the reference frame here, X, Y, and Z, there is the work. So we have how many components? We have 1, we have 2, we have 3, and we have 4 components of work. That means the energy loose because of the system do their own works. We have many works. So from this work, they substitute W dot into this equation. Remember, we have the RTT equation, Renault transport theorem, Q dot minus W dot. They replace W dot with this total work. We have 4 components: the flow work, the shaft work, the shear work, the work due to the motion of from the reference frame. So all these terms, they substitute into this equation. Now this equation become this equation. You can see Q dot minus WS minus W shear minus work due to the frame motion equal to D dt. Right? And suddenly you realize that there is only 3 terms. 1, 2, and 3. What happened to the 4th term? We have 4 components, remember? 1, 2, 3, and 4. But this one is missing suddenly because this one, actually there is a component of this. We call as the flow work. I try to include negative control surface. There is the term here, but this term is basically shifted to the other side, right? They shift to the other side. Why they shift the other side? Because there is the same term. We have the integral of control surface. This term also have the control surface. So they try to simplify the equation. That's why they factorize energy. You can see here. They factorize this term with this term, finally become this term. Right? This is, sorry, this is not the density, this is pressure. Yes, you can see this is pressure. So This pressure divide with density, multiply with density, they try to cancel each other, then you will get this term. This is energy, multiply with density, you get this term back. Alright? This is how they combine all the work inside the control volume. We have 4 components, remember? Flow work, we have shaft work, we have shear work, we have the work due to the motion of control volume. And in addition, due to the energy moving across the control volume, we have some losses. Remember, the loss is surrounding us. For example, your phones, your laptop. You watch the web, you watch my tutorial, you watch my lecture. Alright? So what happened to your laptop or phone for the long time? Is it going to heat up, right? So your machinery, for example, your computer, PC will heat up. So this heat up is because of the loss, right? So this loss can be directly related to this term. Okay. This loss, the loss of energy, remember we have so many loss, right? Whatever design, for example, like a fridge design, like a television design, there is still a loss. And you will notice that there is the star rating on your television, on your fridge, right? There is the 3 star. There are many components. There are 5 stars. So all these stars contribute to the loss, right? When there is for example, there are only 4 stars, that means there are loss. So this loss, so for example, this is control volume. The heat coming to the system and it lost to the system. So the heat going and lost to the system. So for example, the energy of heat. Energy of heat is 100 joule. So what do you think of this loss? What will be the number of joule? Is it the same or different? Or is it increase or reduce? A, for example, is it 100 joule? B, is it like 40 joule? C, is it 120 joule? Okay, which one? What do you think? The energy. Amirul said C, higher than the input. What will be the loss of energy? Actually, it is not, okay, you must be confused. Okay, it's okay. The heat energy can be from the electrical energy, yeah? Okay? It is not you heat this one and then you produce the heat. The heat energy can become from the electrical energy, whatever energy. So basically the energy here will be lost due to the 2 terms. The energy loss plus the internal energy here. Remember that once the heat into the system, this particle will receive the heat energy. Once it receives the heat energy, it will vibrate. It will rotate. So it also produce, it will also receive the energy. So now we can say that the Q, the loss can be in terms of the loss from the heat energy as well as the loss from the internal energy. That's why this term receive the energy, so that means you lost the energy. So the loss of energy is equal to negative Q plus, this is, remember, this is the RTT in terms of the internal energy. So the energy, the answer is V, because this is 40 joule, the rest inside the internal energy, which is 60 joule. So 60 plus 40 is 100 joule. So the energy can be, the loss can be divided into two, the heat loss and the internal loss. You can see in this term, we have this loss and internal energy loss in terms of control volume and control surface. Okay. So after we define this energy equation, right? When the case of steady uniform flow, what mean by steady? Steady means there is no change of time. The steady mean d over dt is equal to 0. Uniform mean the flow considered as average velocity. So we use V average. So from this equation, d dt, we can cancel out the term of time. Cancel. And then this equation, all right? This equation directly convert into this final form. This is final form, right? You must be wonder why there is H loss, right? All right, I would like to show you there is the loss because of this. Okay, remember we have E. E is equal to V squared over 2 plus GZ plus U, right? So this term, they try to substitute this term, they try to expand the energy, they substitute the E with this term, and then together with this term, and then they try to substitute this term. Right. So, okay. So since they consider this is no motion of a control volume, all right, the steady flow with one inlet. Remember, one inlet and one outlet, uniform profile. This is the profile, the uniform profile, and no shear work. They mention no shear. So that means the tau here is equal to 0. So no shear work, 0. The change of time, 0. The following energy equation is used. So they try to simplify the equation, and finally the equation become like this. Right? So Ws is equal to work from the shaft over mg. They divide all this term with mg, mass flow rate with gravity, and then they rearrange the velocity. All right, we have this component. Remember, we have velocity component with respect to one inlet and one outlet. We have the pressure component. This is P, pressure component P2 minus P1 plus Z2. Right, remember we have Z component here. Z2 minus Z1 plus HL. Heat loss is basically coming from this one, internal energy. So to further expand, heat loss is equal to U2 minus U1 over G minus Q over mg, right? And this term is easy to be defined in this equation. So it is easy for you to derive to see that H of loss is actually equal to coefficient of loss multiplied with velocity, average velocity of the flow over 2g. You need to remember this term, heat loss, right? So the loss can be the velocity head and the pressure head. The V squared G is referred to velocity head, and the pressure over gamma is the pressure head. So we have the velocity head. This is velocity head, and this is the pressure head, and then this is the head due to elevation, and this is the loss. Right, and this term is referred to the work. Okay, this is work from the shaft. If the case where the steady uniform flow, negligible of loss. All right, this is case when there is the loss. However, this case there is no loss, negligible loss, and no shaft work. So all this term, all right, all this term cancel. No shaft work. There is no negligible of loss. So we only have this term only. This term is the same with this term. Alright, because they rearrange the velocity 2 at the left side, velocity 1 at the right side. Okay. So I hope you understand, yeah. So basically this is just derivation. I will show you the most very important formula that you need to remember, right? This is we call as the energy equation or the Bernoulli equation, almost identical to Bernoulli equation. All right, so when remember that work consists of, there is the shaft from the pump or the turbine. The pump head is the energy term associated for a pump, Ws mg. Remember that this term, work from the shaft, this is equal to work from the shaft, either from the turbine or the pump. The pump head, HP, is the energy term associated for a pump. If the turbine is involved, energy term is called the turbine head, right? So this term, all right, this term, let's take a look about this term. All right, we consider only the notation only. W dot S over M G. Right. So this term, when there is the pump, for example, this is control volume, there is the pump. So what's the function of pump? Can you comment there? What's the function of pump? What's the function of water pump? Can anyone here please comment what's the function of pump? What the pumps do? The pumps here to increase the pressure. Yes, Fikri Ruzalan. The pump works to increase the pressure, so it will rotate the shaft. So it gives the energy to the system. So the work from the pump is positive or negative? Please comment there. The work from the pump is positive or negative? Anyone? Positive. All right. How about the turbine? Okay, Amirul, this is about coming. Yeah, the one that you confuse is basically the flux. Coming in negative. No, coming in, that means receive. All right. When the control volume receive the energy, it is positive. You can see you put the electric current. For example, this is PowerPoint. Okay, this is power source. You give the energy, right? You give the energy to the system. Is it positive or negative, Amirul? You give the energy. For example, you eat something today. You eat nasi lemak. You eat a lot. You gain weight or you lost weight? Okay. I think, for example, this is someone eating. For example, eat nasi lemak. Nasi lemak. They receive nasi lemak, betul tak? They gain. So bila dia eat banyak sangat, dia akan jadi gain weight. So dia akan gemuk. So this receive positive. Okay? So what happen apabila someone do, what happen when someone, the ideal shape, do work, housekeeping, whatever work they do. For example, housekeeping. Housekeeping. What do you think the weight of the person? Is it gain weight or lost weight? Definitely it will lose weight, right? So this is negative. Same here. When the pump receive the energy, receive the food or receive the energy from the pump, it will be positive. How about the pump? How about the control volume? Give the energy. So what do you think? The work of the turbine, is it giving the energy or gain the energy from the turbine? The turbine. Yes, lost energy. So Hakimi, the control volume giving the energy, lost the energy. So giving the energy, right? This is energy in. Giving the energy is negative. So negative of turbine. So this is rotate. And you save the power. This is battery, for example. So the same goes here. This basically this equation. Alright. This equation. Okay. When there is the pump, for example, when there is the pump and turbine, the pump is giving the energy, remember? So we have the head of the pump plus, you just continue here. I think I try to write it here. if there is the pump, you have to plus heat of pump. If there is the turbine, you have to, this is the turbine. Turbine is minus. So you have to plus minus of heat of turbine. So this equation is related to the energy equation. Alright. Remember that we have Ws over mg. So from the previous equation, Ws over m dot g, if the equation reflect to heat of the pump, plus v squared over 2g plus gz. Let me check the equation. Alright, P. Okay. We have the P. We have P here. Over gamma plus Z1 equal to, remember that this is pump positive, and if there is the turbine negative, H of turbine. This term I translate to this term. So become H of turbine positive. Okay. Plus V2 squared over 2G plus P2 plus Z1 plus heat loss. Right? Okay, never mind. Okay. So basically this HP related to the work done over mass flow rate times gravity. So when it involves of the pump, right, we multiply this one with the efficiency of the pump. So efficiency of the pump is equal to HP equal to efficiency of the pump multiplied with heat of pump equal to work done of the shaft over mg. In order to get the work of the pump, okay, sorry. Okay. Alright. Okay. So this one, alright, this is heat of pump. This is heat of turbine. Alright. In order to get the turbine efficiency, we multiply this one with the efficiency of turbine. Alright. So remember, we have the control volume, we have the shaft. Right. In order to know the efficiency of this, we have to multiply the efficiency of turbine. So HT, this is HT, yeah. Multiply with efficiency of turbine. Thus, in order to get the power generated by the turbine is W of turbine, this is W of turbine, equal to mg H the efficiency of turbine. So this equation is the same with this equation. Alright, this one Gamma G is the same with this one. Alright, in order to get the power required by the pump, remember the pump need energy to give to the control volume. So it required the power. So this is HP. So H of pump, right, is actually divided with the efficiency of pump because it required to be the input equal to work of pump, the same thing, mg. So in order to get WP, it is actually m dot g HP over efficiency of pump. So you can see this term directly related to this term. Okay. So if the flow, for example, this is the third case, if the steady non-uniform flow, what do you think of steady non-uniform flow? Like this, yeah. The steady mean the change of time equal to 0. The non-uniform mean we consider the shear stress. There is the work from the shear. So non-uniform means this is the pipe flow. It become like this. We have the velocity profile. This velocity profile is non-uniform. Alright, uniform means the same. This is uniform. Once uniform, we can use the average velocity. But non-uniform, alright, we have to add the kinetic energy correction factor. Alright. So this, if the case, when you try to solve the case of non-uniform flow, alright, you have to apply the kinetic energy correction factor, which is alpha. So the alpha formula is integral of velocity profile. So once they will give you the velocity profile, the power of 3 dA, the cross-sectional area over the average velocity 3 over A. So this term, derivation of this will contribute to the alpha. They try to change alpha here to become the subject, and this is the final equation. And if you have the energy equation, remember that this is your energy equation. The one that I show you the derivations. This is the head of the pump. It is positive. This is head of turbine. Previously, it is negative. We transfer to the other side, become positive. And this is the correction factor velocity profile 1. And this is correction factor velocity profile 2. The rest is the same. This is the head due to kinetic. This is the head due to pressure. This is the head due to elevation. Right? This is loss. Remember the loss K V squared over 2G. Okay. So all this is the example I will show you in the tutorial. Please do join my tutorial on Thursday. Okay, I will explain more on this. So I think that's all about this chapter. I lecture you on two big topic, which is the conservation of mass and conservation of energy. Remember why we have the conservation of mass? It is because the extensive property number one is mass. That's why we try to solve the conservation of mass using Renault transport theorem, RTT. In the RTT, we have two components. We have the control volume, the change of control volume, and the flux property on the control surface. All right. From the derivations of the control volume and control surface, we get the conservation of mass, which is rho 2 V2 A2 equal to rho 1 V1 A1. That is the conservation of mass. If the flow is incompressible, the change of density is 0. So we can cancel the density. So it becomes A1 V1 equal to A2 V2. So A1 V1 is the volume flow rate. And the density rho AV is the mass flow rate. The mass flow rate, the symbol of mass flow rate is m dot. All right. The volume flow rate is the Q only, not the Q dot. The Q dot for the heat transfer. So after you understand the conservation of mass, we go for the next extensive property, which is energy. The energy coming from the three terms: the kinetic energy, potential energy, and internal energy. So from those energy, there is the work. The work done to the system is negative because the control volume release the energy. They do their work. So it release the energy negative. So the work here, there are four components of work. The first is the flow work due to pressure. The second one is the shaft work due to the pump and the turbine. And the third term, work related to the shear stress, wall friction of the pipe. And lastly, the work due to the moving control volume from one point to the another. So when you try to substitute all the four terms of work into the energy equation, it will become very expanded energy equation. And we consider the internal energy and the heat as the loss. So when you consider there is the loss, so you simplify the equation, you expand the energy E equal to kinetic energy, potential energy, and internal energy. Finally, you will get the final equation. Please use, I think you need to remember this. This is very easy. The last term that you have to know is only this. What you learned previously, what you need to know is this only. It's very simple. HT plus V1 squared over 2G plus P1 over gamma plus Z1 equal to heat of pump plus V2 squared over 2G plus P1 over gamma, P2 plus Z2 and loss. Alright, only this term you need to remember. Right, it's very simple. When there is no pump, cancel pump. When there is no turbine, cancel turbine. When negligible loss, cancel negligible loss. When the same height, cancel when the same elevation, cancel the Z1 and Z2. When the atmospheric pressure, cancel pressure. When the flow is very slow, cancel the velocity. And we have the H, we have the HL, loss due to the heat and the internal energy. We can consider as K is the coefficient, loss coefficient multiplied with V, average velocity of the pipe, over 2G. Very simple. Only this one, you can solve anything related to the Bernoulli equation, related to the energy equation. Please bear in mind, only this equation you need to remember, 1 and 2. Everything is simple, all right? Previously, I show you the derivation, step by step on how to get this equation 1. Okay? So far clear? Everyone? This equation? Amirul Hakim. So far you clear, yeah? Please remember, please write it down, the equation number 1 and equation number 2. Very simple. This chapter focus on this equation. Alright? This is energy equation. The second one, right? This is energy equation. This is mass equation, which is rho 1 A1 B1 equal to rho 2 A2 B2, and A1 B1 equal to A2 B2. Remember, this is very simple term. This is the mass flow rate, and this is the volume flow rate. The first chapter we learn about this one. The first subtopic we learn about conservation of mass lead to this equation. The second we learn about the energy equation lead to this equation. Now I try to summarize for you. You will be dealing only this equation later on. All right. So I think you need to understand on how to derive. It's very simple. When you try to derive this extensive property, remember to apply RTT, Renault transport theorem. Consists of change of the control volume and the flux property. Alright, so only this term. Please write it down and remember, rho AV is for the gas, AV for the water. Yeah, when there is the question asked, you need to identify the medium. Is it water or gas? If the water, you use this equation. If the gas, use this equation. All right. Okay, do you have any questions so far? Before we end our session, all right? On tomorrow, I will proceed to the momentum equation. Alright, basically I have prepared you one video, the lecture of momentum equation, and I already uploaded in the e-learning system. So tomorrow I have the seminar, and I unable to give a presentation to you on the momentum equation. However, I have prepared before this. I have prepared the momentum equation lecture in the video. All right, I have uploaded the material, the momentum equation. I show you how to derive this one and show you how it forms the steady equation. All right. So tomorrow we don't have any lecture. I have the seminar full day. All right, so I'm so sorry, but I have prepared the video, the momentum equation. Please spare of your time during that lecture, 1 hour tomorrow. Please view this lecture, momentum equation. I have posted in the e-learning. Okay, so far okay, right. So I will post as well the attendance in the WhatsApp group. Okay. So I hope tomorrow you scan your attendance, and please spend 1 hour to read my lecture note on the momentum equation. I have prepared the lecture note in the e-learning. Please access it. Okay, I think that's all about today's lecture. Tomorrow we don't have any lecture because I have the seminar full day, and we have the tutorial. Okay, I think that's all about today. So do you have any questions so far? I will post